block elements. Yeah, block elements. Or inner transition so what is the definition? The elements in which the last electron goes to penultimate penultimate means one before last. Antepenultimate means two before last. Antepenultimate or n-2 f orbitals are so-called f block elements or inner transition elements. See, here you do not have any separate definition of inner transition elements as we have done in case of the transition elements. And with transition elements, we have given a separate definition. First, we have given a definition of d block elements, mentioning that where the electron goes to the n-1 d orbitals. So we call them as d block elements. Then again, we have defined the transition elements where you find either in their atomic state or in any of their ion or oxidation state. If they have unpaired electron, we call them transition elements. But in case of this inner transition elements or F block elements, no such different definition is being given. This is the definition. Okay. So what should we write now here? It is placed at the bottom of the periodic table separately. Now we know there are excuse me, just a minute. Huh? There are two series. Two series of F block or inner transition elements. Blue আছে তো না খালি লিখব অল্পই আছে lanthanoids or lanthanides. And second one is actinoids or actinides. So now we'll start with okay. So I'll write down the general electron configuration first of the F block elements. So general electronic general outermost shell electronic configuration. Okay, it is NS2 N minus 1 D 0 or 1 N minus 2 F 1 to 40. Okay. So now I'll go for lanthanides. So I can define in two ways. Yeah? You can call the whichever you like, you remember. The series involving the filling differentiating. Differentiating means what? It is by which you can differentiate one element from another. Filling differentiating electrons in 4f orbitals is called lengtheners. This is one definition, or you can write. It is a series of 14 elements occurring after lanthanum is called in your book. No, they have given lanthanoids, so you please write lanthanoids. Huh? So you write here lanthanoids. Lanthanoids. It begins with cerium and ends with lutetia. So what will be its electronic configuration? It will be 6s2 5d 0 or 1 4f 1 to 40. Lanthanides and actinides we are not going to study in detail. Okay. So now we are going for oxidation. The most common oxidation state of lanthanoid is +3. See here, why it is plus? This is the one which differs from transition metals. Transition metals, most common oxidation state is +2, and here it is +3. Why it is +3? See here. This electron goes along with this. So 2 + 1, 3. In very few cases, you find is D0 is there. Okay, so if it is D0, then you can get +2 also. they also exhibit oxidation states of +2 and +4. Why does it happen? This type of oxidation state occurs in just to attain stable electron configurations. They also exhibit oxidation +2 and +4. These oxidation states +2 and +4 appears to attain stable electronic configuration of F0, F7 or F40. In some of the elements. So all elements do not show. Okay. See here, before discussing atomic radii and ionic radii, I have discussed oxidation region is there. Huh? Atomic and ionic radii. Atomic and ionic radii. There is a regular decrease in the sizes. Sizes means what? Sizes of atoms or ions. It is atomic and ionic radii. Of lanthanoids. As we move from left to right across the series. This phenomenon is here you please give a gap. Right here that is, we'll put square bracket here, and here you'll put L N 3 plus, put a comma. Or I can write it here. My hand got totally spoiled. N Ln 3 plus. See, Ln is not an element. It is an abbreviation of lanthanides. Okay? Ln 3 plus. Because when you talk about ions, the stable of ion is plus 3 or 3 plus. This phenomenon is called lanthanide contraction. See, it did not happen like in tension elements. What did you find? It was like this. But in case of lanthanides, it is like. So in this case, it is not like tension elements that gradually decreases again increases. No, it decreases. But so this phenomenon is called lanthanide contraction. This lanthanide contraction I will discuss later. Why it is like this? Now, ionization. This I will discuss separately. Ionization the first and second ionization enthalpies of lanthanoids are almost equivalent to calcium. This is very interesting. Why? Calcium is in the top of the periodic table. Lanthanum is at the bottom. So as far as the periodic table, we know that if you go down the group, the sizes of the elements increases. But here we find that the size has decreased. Okay, that is because of lanthanide contraction. So because of that, lanthanides show similar reactivity of that of calcium. Calcium is highly reactive. So lanthanides are also highly reactive. This implies that lanthanides are as reactive as calcium. Then I'll write next one is formation of colored salts. See, why D block elements form colored salts? I told you, because they have unpaired electrons. So it will be D1, D2, D3, D4, D5. Then after that, up to D9, you will find unpaired electrons are there, either in their elements, in their ions. So in case of lanthanides, number of unpaired electrons are more because there are 7 f orbitals are there. So same phenomenon is there. So in d block elements, what did you say? That transition elements ions are colored because of the presence of unpaired electron in their d orbitals, which absorb visible light and undergoes DD transition. Here every word is same, but in case of instead of DD transition, we'll write here FF transitions. We'll write now here lanthanoid ions or lanthanoid ions or salts, because salts are from ions only or salts. As the question comes, you will answer it. Or salts are colored due to the presence of unpaired electrons in their f orbitals, which undergo FF transition by absorbing electromagnetic radiations from visible light. So please remember this one. This is important. Now see here, same condition can be applied for the magnetic properties. So right now here magnetic properties. But one thing is that here, that if you want to calculate the magnetic moment for the lanthanides, you cannot use the same equation that you have used for d orbitals, that root over n into n plus 2. Okay. So now we can write here. So please remember, this is important. So magnetic property. Lanthanoids ions having unpaired electrons are paramagnetic, while those having paired electrons are diamagnetic. See, the magnetic behavior of lanthanides differ from their. I'll write now. The magnetic behavior of lanthanoid ions differ from transition metal ion. Transition metal ions. See, in transition metal ions, we only take into consideration the spin only magnetic moment. But in case of lanthanides, it comprises of both spin as well as orbital motion. As lanthanoid magnetic moment is due to both electron spin and orbital motion. Please remember for your entrance exam, this one, orbital motion. But in case of transition metal ions, it only depends upon electron spin. Now we'll go for is chemical reactivity. Chemical so right now, yeah. Due to similar electronic configuration and their existence in mainly +3 oxidation states. Lanthanoids show very similar chemical properties. Right. Due to lesser ionization enthalpies, these are highly reactive. They react with water and acids to liberate hydrogen. They lose their metallic luster when exposed to air. What does it mean? They react with oxygen and nitrogen in the air. Okay, so they react with almost all non-metals. Huh? Okay, so here we are not going to write the reactions of lanthanides, just like we have done in case of the D block elements. I'll write it as summary. Okay. Don't write now. See here, how I'm writing. Length. We'll write the property like this. Here I'm right. Dilute. Because of the cold, no control on head. Dilute acid. It can be, dilute acid is what? It can be HCl, it can be sulfuric acid like that. So what it will give you? It will give you salt plus hydrogen. Okay? Water. Heat. It will give you lanthanum hydroxide, hydrogen. Hydrogen, heat. It will give you lanthanum hydride. If you have taken halogen, fluorine, bromine, iodine, it will give you lanthanum halides. It reacts with oxygen to give you lanthanum oxides. It reacts with nitrogen. See, valency of lanthanum is 3, nitrogen is also 3. So it will give you lanthanum nitrides. It reacts with sulfur. Okay. It will give you then if it reacts with carbon, it gives you a series of different carbides. It gives you Ln3C, Ln2C3, LnCb. So I'll now, after that, I'll write down some lanthanum salts are found to be good, strong reducing agent and oxidizing agent. First I'll explain, then I'll give it to you. Filter কিন্তু আমার চলতে আছে।
Done, sir.
Good. Now we'll see the redox reaction of by lanthanum salts. That I should have discussed with you oxidation state, but I did not. So I'll discuss separately. Redox reactions of lanthanoid ions or salts. See, the common oxidation state of lanthanide is +2. Sorry, +3. All right, but we have seen the lanthanides also exhibit +2 oxidation state and +4 oxidation states. Common oxidation state of lanthanoids is +3. However, they also exhibit oxidation states of +2 and +4. Right now here. Right now here, +4 oxidation state. Right now here, cerium and terbium show oxidation state of +4 along with +3 due to F0 and F7. F7 is what? Half filled. Configuration. These ions are oxidation oxidizing in nature. Why? See here. Ln, alright, like cerium plus 4. So which is the stable one? Stable oxidation state is what? Plus 3. So it will take one electron from others and it will attain plus 3 electronic configuration. Please remember. Ceric ammonium nitrate is a strong oxidizing agent. Please remember for your entrance exam, dear. So both terbium 4 plus and cerium 4 plus are strong oxidizing agent. If you wish, you can write also here. Tb plus 4 plus electron. Tb plus. Then B plus 2 oxidation state. See, whatever I have learned in my life, I am telling you. Europium. And ytterbium. YB. Exhibit plus 2 oxidation state. Along with plus 3. These are strong reducing agents. Why? See here. EU plus 2. But which is more stable? It is plus 3. So in that case, what is going to happen? It is immediately going to lose 1 electron. Okay. So they are reducing agent. Please remember.
Answer.
Okay. So now we'll go for lengthened contraction. Hey, Vansan, in your school, you selection exam is over or what? Or form fill up?
Sir, we don't have selections, sir.
Achha, then what about the filling up of form?
We are doing it now.
Online.
No, sir.
Then you going to school.
Yes, sir.
Okay. And the practical to khatam, na? Did you do any practical?
We did, sir. I don't think we have finished practicals. We still have many to do.
What are those practical you have done?
We did identification of salts.
Acha.
Then yesterday, or day before yesterday, we did titration.
Acha.
That's it.
So now we'll go for lengthened contraction. If the definition comes, only one sentence you have to write. The gradual decrease in atomic radii of the lanthanides from left to right across the series is called lanthanoid we call it lanthanide contraction. This is the definition. No, but why does it happen? So right now here, cause. Okay, finish writing, then I'll tell you. And in army school, practical finish. Kilo Aparajita? Hello. তো প্র্যাকটিক্যাল নাই এবার
বলেছো করাবে
আচ্ছা ঠিক আছে হবে now cos see here that I told you that S block is smallest S block is smallest then comes P block then comes D block I don't know the shape of the F orbitals assume it is like this so it will be like this na and this is the nucleus see here nucleus electron is here nucleus electron is here nucleus electron is here and in this case electron is here see here so these electrons are very very far almost lie near to the boundary of the atom When this is what happened, in this case, you will find that electron will not be able to neutralize the positive charge of the nucleus, and gradually, the nucleus is going to build up lot of positive charge. So because of that, what will happen? Nucleus will start pulling the electron. So what should we say? In other words, we cannot say like this, cancellation, all this thing. We'll say that F orbital is having, F orbitals are very large in size, and due to that, the F electrons cannot screen the nuclear charge, which results in the contraction of the atomic radii. So we'll write now here. So very large size, what we call in our quantum mechanical condition, we call it diffused. All right. Due to very large size of F orbitals, the F electrons cannot screen the nuclear charge effectively, which, okay, I will not make the sentence very long. We'll write a full stop. This leads to accumulation of large nuclear charge, which this leads to the accumulation of large nuclear charge. As this, let me make the sentence in a better way. This leads to accumulation of large nuclear charge by which contraction of atomic orbitals by which contraction of atomic radii takes place. This phenomenon is called Lenoid Contracts. Okay. Consequences of Lenoid contraction, I'll do it on Saturday because I need not, only 5 minutes are there. So there are 3 consequences are there. I have to explain, then I will write down for you. And actinoids will finish on Saturday. So next week I'll start coordination chemistry. But coordination chemistry definitions, all these things will read, okay? Thing which requires explanation, that there I'll write less and give you more explanation.